Thank you very much for tuning in to my virtual webinar about composite ab initio methods. Not every day I get a chance to talk to leading physical chemists, so I would like to start with a very relevant topic, the Journal of Chemical Physics Letters. The journal was established over 50 years ago, and the scope of the journal covers all aspects of physical chemistry. So, for example, developments in theoretical and computational chemistry, new experimental methods, nanostructures and nanomaterials, energy conversion and storage, biomolecular systems, polymers, and gas phase chemistry. The editors of the journal are David Clary from the University of Oxford. David has been one of the leading editors of the journal for over 20 years now. We also have Benjamin Dietzek from the University of Jena in Germany and Kelly Han from the Dalian Institute of Chemical Physics in China. I joined the editorial team recently, and I'm very happy to be on board. In this context, I should also mention Michio Komura, who has been an editor for many years and has recently retired. Over the years, Chem Phys Lett has published many papers in the development of theoretical and computational methods, and I would just like to mention some of these papers here. I will also talk about some of these papers in quite some length today. The paper that developed the so-called CCSD parenthesis T method was published just over 30 years ago by Krishna Ragavachari, Martin Head Gordon, John Popel, and others. This method is known as the gold standard of computational chemistry and is of key importance in composite ab initio methods. One of the papers that developed the polarizable continuum solvation model was also published in Chem Phys Lett in 1996. A key paper that developed basis set extrapolations, which are also of key importance in composite ab initio methods, was published in 1998. The paper that developed the CAM B3-LIP method was published in 2004. In the same year, a number of papers that describe explicit correlation methods were published in Chem Phys Lett. In 2011, Don Truller published an important paper describing the Minnesota functionals. And if I can get away with mentioning one of my own papers that was also published in 2011 and develops a thermochemical database of total atomization energies. Chem Phys Lett has a very high visibility around the world, and this is particularly true for countries like the United States, China, and Germany. And I would like to show you some of recent papers that are fairly highly cited. I will flick through these papers fairly quickly, but this is just to show that papers published in Chem Phys Lett can be highly cited, and submissions from Australia and New Zealand are very welcome. So let's move on to an introduction to composite ab initio methods. In this short presentation, I won't be able to go into too much detail. I will only be able to give you a taste of the topic. So I'm listing here a number of excellent reviews that cover composite ab initio methods, and you are very welcome to check them out. Composite ab initio methods are used for obtaining highly accurate thermochemical and kinetic properties. So, for example, things like reaction energies, enthalpies of formation, reaction barrier heights. They can also be used for calculating highly accurate molecular structures and spectroscopic and electrical properties. So there's a very clear chemical motivation for using composite ab initio methods when we want to calculate these chemical properties with high levels of accuracy. A theoretical motivation for using composite ab initio methods is for calculating highly accurate chemical properties for the parameterization of more approximate theoretical procedures, most notably for the development of better and more accurate density functional methods. It's always good to have a slide with a Feynman quote in any scientific presentation, so here's mine. It doesn't matter how beautiful your theory is, If it doesn't agree with experiment, it's wrong. And I imagine that Feynman was implying the word reliable here as well. So in this presentation, we will see how we can benchmark the most accurate quantum chemical methods against very, very accurate experimental data. But in contrast to, say, 30 years ago, when supercomputers were not as strong and our theoretical methods were not as refined as they are today, we would normally see this interaction between theory and experiment. So the experimentalist would go to the theoretician and say, your calculations disagree with our experimental results, therefore your theories are wrong. Today we have a more balanced relationship between theory and experiment, and often it can go the other way. So the theoretician would go to the experimentalist and say, your results disagree with our very accurate calculations, so go and check your experimental results again. But it is important to mention that even though we have a more balanced relationship these days between theory and experiment, this does not mean that every result that we obtain with density functional theory, or even with a composite ab initio method, is necessarily correct. And we always have to make sure that we are obtaining the right answer for the right reason. So how can we compare between theory and experiment? In order to visualize this, we can imagine a three-dimensional cube. Here we have our wave function axis. So we start from the Hartree-Fock wave function, and we include more and more electronic excitations in the wave function. Here we have our basis set axis, and we can start from a minimal basis set and expand the wave function using larger and larger basis sets. If we use an infinitely large basis set, and we include all possible electronic excitations in the wave function, then by definition, we calculate the exact non-relativistic electronic energy. Now, in order to compare this energy with experiment, we have to consider secondary energetic contributions, so things like the zero-point vibrational energy, relativistic corrections, and deviations from the Born-Oppenheimer approximation. If we calculate all secondary corrections with a high degree of accuracy, then we obtain a highly accurate theoretical energy that we can directly compare with experiment. Now, the point of this slide is that composite ab initio methods can do all of this. So they are methods that were specifically designed to calculate all of these steps with a high level of accuracy and to obtain accurate energies that we can directly compare with experiment. Well, now I got myself into trouble because the computational chemists in the audience will say the only systems for which you can include all possible electronic excitations in the wave function and run these calculations with a very large basis set are very small molecules like diatomic and triatomics. So for larger systems like benzene, naphthalene, or even larger, how can we obtain highly accurate energies that are close to the exact solution? Well, this is where basis set extrapolations and other basis set acceleration techniques come into play. So let's look at what is computationally feasible for a fairly small molecule, propane, with 20 valence electrons. So here we see the Pople diagram with the wave function axis here and the basis set axis here. And the key point to note in this Pople diagram is that as we include more and more electronic excitations in the wave function, the computational cost increases in an exponential manner, and we can run these calculations only using smaller and smaller basis sets. So by the time we include all possible excitations in the wave function, we can afford these calculations with a very, very small basis set, which for propane would be smaller than a double zeta basis set. So if this is the computational space available to us, how can we obtain energies that are close to the exact solution? So this is where basis set extrapolations come into play. And in the composite methods that I'm going to introduce today, we use two-point basis set extrapolations. And that means that for each of the energetic components, we will run an additional calculation using a slightly smaller basis set. So we run all of these additional calculations that have a lower computational cost than the calculations that we already ran with the larger basis sets. Now, because of the systematic behavior of these basis sets, in these cases, the correlation consistent basis sets, we can take these two energies and extrapolate them to the complete basis set limit or the infinite basis set limit. So we can do this for all of the energetic components, and a key feature that the composite methods rely on is that as we go to higher and higher excitations, the basis set convergence is accelerated, and we need smaller and smaller basis sets in order to approximate the infinite basis set limit. So now we are going to take all of these energy components, and we can sum them up and obtain an estimate to the exact non-relativistic electronic energy. So generally speaking, composite ab initio methods could be divided into two categories: the more rigorous non-empirical methods. These methods involve calculations of at least the CCSD parenthesis T level, but often they include contributions beyond that. These energies are extrapolated to the infinite basis set limit using very large Gaussian basis sets, and secondary energetic contributions like relativistic effects and deviations from the Bohr-Oppenheimer approximation are taken into account explicitly. Methods of this type include the Weizmann-N methods of Jan Martin from the Weizmann Institute, the heat protocols of Gauss and Stanton, the Feller-Peterson-Dixon methods, and the CCCA methods of Angela Wilson. Now, these composite methods are very rigorous, they are very accurate, but they are also applicable to fairly small molecules, and I will talk about this in one of the next slides. Empirically corrected composite ab initio methods involve lower-level CCSD parenthesis T calculations. These energies are not extrapolated to the infinite basis set limit, but rather they use basis set correction terms obtained from Moller-Plesset perturbation theory. Secondary energetic effects are not always taken into account explicitly, and this means that in order to obtain high accuracy, these methods need to include empirical terms that are parameterized against accurate experimental data. Because these methods are computationally much more economical, they are applicable to much larger systems than the non-empirical methods and are therefore very, very useful. Methods of this type include the Gaussian N methods of Krishnan Bhaggavachari and co-workers. In this context, I should also mention the G4MP26X method of Boon Chan and Leo Radem, and also the CBS methods of Peterson and co-workers. Here I will mainly talk about the non-empirical methods. These methods can again be divided into two basic categories: what we call post-CCSD parenthesis T methods that try to approximate the exact energy, and CCSD parenthesis T methods that try to approximate the CCSD parenthesis T energy close to the complete basis set limit. The accuracy of the post-CCSD parenthesis T methods is normally within plus or minus 1 kilojoules per mole, and the target accuracy of the CCSD parenthesis T methods is normally within plus or minus 1 kcal per mole. So let's ask the following question: how well do post-CCSD parenthesis T composite ab initio methods perform relative to very accurate experimental data? And when we are benchmarking these very accurate theoretical procedures, we are going to do it for total atomization energies. The reason for that is that total atomization energies are one of the most challenging chemical properties for electronic structure methods. A total atomization energy is the energy required to break all of the bonds in a molecule and to separate it into the free atoms. So in a molecule like phenol, for example, we have 6 aromatic CC bonds, 5 CH bonds, 1 CO bond, and 1 OH bond. And if you sum these bond energies up, you will quickly reach energies exceeding 5,000 kilojoules per mole. And the target accuracy of post-CCSD parenthesis T composite methods is plus or minus 1 kilojoule per mole. So this is quite remarkable. We would like to calculate an energy that can exceed 5,000 kilojoules per mole with a target accuracy of only 1 kilojoule per mole. Okay, so let's see how we go. Now, when we benchmark these highly accurate theoretical procedures, we have to use highly accurate experimental data. Here we would like you to use experimental total atomization energies with error bars that are equal or smaller to 0.2 kilojoules per mole. Now, such highly accurate experimental data is only available for a fairly small number of systems. Here we have gathered a set of 35 experimental total atomization energies with error bars that are equal or smaller to 0.2 kilojoules per mole. And when we benchmark one of our post-CCSD parenthesis T composite methods, one of the WN methods, in this case we're benchmarking the W4 method, we get a root mean square deviation of 0.36 kilojoules per mole, which implies a 95% confidence interval of 0.7 kilojoules per mole. This means that any total atomization energy that is calculated with the W4 composite ab initio methods will have an error bar of plus or minus 0.7 kilojoules per mole, just below the 1 kilojoule per mole mark. So this is really great, but the downside is that these methods are computationally so expensive they are only applicable to fairly small molecules. So molecules like acetic acid, glyoxal, CF4, and so on. So these methods are indeed highly accurate, but they have limited applicability. So let's move on to methods that are still post-CCSD parenthesis T methods, but are computationally less expensive. These methods are called CCSDT parenthesis Q composite ab initio methods, and in these methods we neglect all of the terms above the quadruple excitations, and the connected quadruple excitations are treated in a quasi-perturbative manner. These approximations will result in a significant reduction in the computational cost, but it has to come with a warning. So here we see the errors that will result from neglecting these high-level terms for a number of highly multi-reference systems. So for example, for ozone, a very famous multi-reference molecule, neglecting these high-level terms will result in an error of about 2 kilojoules per mole, and for C2, it will result in an error of about 3 kilojoules per mole. So the CCSDT parenthesis Q composite ab initio methods can no longer achieve accuracy within 1 kilojoule per mole for total atomization energies of highly multi-reference systems. Here we see a number of composite ab initio methods from the Weitzman N family that belong to this category. So we have methods like W4 light and W3. Here we see the root mean square deviations that we obtain against highly accurate experimental total atomization energies and the associated 95% confidence interval. So while we can no longer achieve 95% confidence intervals that are smaller than 1 kilojoule per mole, we still obtain very respectable error bars with the CCSDT parenthesis Q composite ab initio methods. Here we see the applicability of CCSDT parenthesis Q composite ab initio methods. So we can see that they're applicable to much larger systems like benzene, the phenyl radical, pyridine, and even C2Cl6 and the SF6 anion. Nevertheless, most chemists would still say that we can't do a lot of chemistry with these systems. So let's move on to composite ab initio methods that are computationally more economical and are applicable to even larger systems. So let's move on to the CCSD parenthesis T composite ab initio methods. These methods are much more popular and are applicable to much larger systems than the post-CCSD parenthesis T methods that we talked about so far. Here we see the computational scaling of the post-CCSD parenthesis T terms. We can see that they scale to the power of 3, 4, and 5 with the number of electrons in the system, and to the power of 5, 6, and 7 with the number of basis functions in the system. In contrast, the CCSD parenthesis T method scales to the power of 2 and 3 with the number of electrons, and to the power of 4 with the number of basis functions that we are using. So the CCSD parenthesis T method is applicable to much larger systems, but we will see that this reduction in computational cost comes with some sacrifice in the accuracy and the applicability of these methods, especially to multi-reference systems. One of the reasons why the CCSD parenthesis T method works so well at a modest computational cost is because the systematic error cancellation between the neglect of the higher order triple excitations and excitations beyond that. This error compensation works remarkably well for systems that are dominated by a single reference configuration, and for those systems, this approximation would normally result in errors that are up to 1 kcal per mole from the full CI/CBS limit. However, for multi-reference systems, we have to be very careful when we apply the CCSD parenthesis T method or any composite ab initio method that is based on the CCSD parenthesis T method and does not go beyond that. So here, for example, we see errors for highly multi-reference systems that result from the neglect of terms beyond CCSD parenthesis T. So we can see that these errors can reach up to 20 kilojoules per mole for highly multi-reference systems. So for example, for ozone, which is a highly multi-reference system, the neglect of post-CCSD parenthesis T terms will result in an error of about 12 kilojoules per mole. This is an unacceptably large error for a composite ab initio method. And for large carbon clusters, we will get errors that are even larger than that. So it would be very useful if we could assess the degree of multi-reference character of a system before we apply a CCSD parenthesis T based composite ab initio method to it. Such a diagnostic exists. It's called the percentage TAE parenthesis T diagnostic. I don't have time to explain how this diagnostic works, but it is described in these references here. So now that we know not to apply CCSD parenthesis T based composite ab initio methods to multi-reference systems, let's look at the applicability of these methods. So for example, the Weizmann-1 composite method is applicable to systems with up to about 20 carbon atoms. So we were able to apply it to dodecahedrine, coraniolene, and sumanine. And we were able to apply the lower cost G4MP2 composite ab initio method to systems as large as C60. We were also able to apply the W1 method to DNA bases like adenine and guanine, and to amino acids like arginine, histidine, and phenylalanine. So let's look at the performance of composite CCSD parenthesis T methods. And here we will examine the performance of W1 theory. We benchmark the performance of this method against a diverse database of 183 total atomization energies, all obtained at the full CI/CBS level of theory. Now, these 183 total atomization energies were obtained for systems that we deem not multi-reference according to the percentage TAE parenthesis T diagnostic. Now for this database, W1 theory attains a root mean square deviation of 3 kilojoules per mole, which implies a 95% confidence interval of about 5 kilojoules per mole. This means that the error bar that we can attach to any total atomization energy that we calculate with W1 theory is plus or minus 5 kilojoules per mole. On my last slide, I would like to show you an example of where W1 theory played a key role in a critical evaluation of experimental data. So here we see the experimental heats of formation of benzene, naphthalene, and anthracene. We can see that they sit on a straight line, and they are all associated with fairly small error bars of below 3 kilojoules per mole. Now, this is a homologous series, and we can pass a straight line through these points to get an estimation of the heats of formation of tetrazene. And if we do that, we get an estimated heat of formation for tetrazene of about 300 kilojoules per mole. Now, the problem is that the experimental heat of formation for tetrazene is over 40 kilojoules per mole above this estimated value. And to make things worse, the error bar associated with this measurement cannot possibly account for this very large difference. So in a case like this, it's very useful to be able to apply a composite ab initio method to calculate these heats of formation. And we did that with W1 theory. And for benzene, naphthalene, and anthracene, we get a fairly good agreement between theory and experiment. And for tetrazene, our theoretical value is much closer to the estimated value from the homologous series. So these calculations suggest that the error bar associated with this measurement is much larger than what we see here. Okay, so I see that I'm running out of time, so I would like to very quickly wrap up and thank the RACI Physical Chemistry Division and especially Laura McCamish and Taki for organizing this webinar series. I would like to thank the Australian Research Council for a future fellowship and our national supercomputer facilities. Above all, I would like to thank you for tuning in to this webinar, which should be available online afterwards. Thank you.
So I'm going to tell you today a bit different to what Amir just told you. This is going to be about experimental physical chemistry. So I'm going to talk about the effect of water on electrochemical processes in ionic liquids and why it's really important, particularly when you want to apply ionic liquids in applications, and why we really need to understand what's happening at the electrical double layer. So ionic liquids, or room temperature ionic liquids, have been used as replacement electrochemical solvents since about the beginning of the century. And I've used them over the last about 8 years to try to use them as electrochemical sensor materials. So they can be used in various different electrochemical applications, including batteries, supercapacitors, and actuators as well. And this is because they have lots of favorable properties, which include wide electrochemical windows, high chemical and thermostability. They're intrinsically conductive because they're made entirely of ions. And they're very tunable because you can change the chemical structure of the ions. And one of the most important properties for us is that they are non-volatile. So they have very low volatility, meaning we can use really tiny amounts of ionic liquids and we don't have to worry about evaporation of the solvent. And they also have very good solvation properties, which is excellent for being able to sense most chemical species. So you can think of an ionic liquid in the same way as a molten salt. So most of us should be familiar with sodium chloride. And these have the sodium and the chloride ions have similar size, and they pack very well together in this lattice structure, and they have very high melting point. Ionic liquids are similar, but they have normally one of the ions is much larger and asymmetric. So you can see here when you replace the sodium with a quaternary ammonium, you don't have this nice lattice structure, and the melting point is 80 degrees. So this is technically an ionic liquid because the melting point is below 100, but we are really interested in using room temperature ionic liquids, and you normally change the anion to a larger structure, and this makes the melting point below room temperature. So how we use them in our experiments is for our sensing applications, we use these very miniaturized planar electrode devices, and you can see just how small they are on the end of my fingertip. So you have the 3 electrodes, the working, the reference and the counter electrode, all printed within a very small area. And then you can see the side view at the bottom. We cover the electrodes with just a 1 microliter droplet of ionic liquid, so very small. And we then have, for our gas sensing experiments, we have a gas flowing continuously over the ionic liquid. We have a partitioning from the gas phase into the liquid phase. And then once we have equilibration, we can apply a potential at the working electrode. The gas diffuses to the electrode, and then we can oxidize or reduce that gas, and we get a current response. And we can relate the size of the current response to the concentration of the gas in the gas phase. And so we've done a lot of work looking at different gas mechanisms and the analytical utility, how low can we go? But we typically have done this all in dry gas environments. But in order to have a sensor like this one, which is open to the environment, we need to know what effects humidity have on the electrochemical response. Because obviously, wherever you put your sensor, you're going to have some kind of background humidity. So in this talk, I'm going to try to answer the questions, how does water or humidity affect the electrochemical response of dissolved species in ionic liquids? And also, does the structure of the ionic liquid cation or anion have any influence? So I'm first going to talk about the oxygen reduction reaction. And we chose to look at this because oxygen is quite an easy gas for us to detect, and it also changes its mechanism in the presence of water. So all of the work I'm going to talk about today has been done by my PhD student Simon, and Simon's actually available in the chat. So if anybody has any quick questions, Simon's happy to answer any of these. So oxygen reduction in dry ionic liquids is known to follow a 1 electron reduction to the superoxide radical. And this is reversible. So if you look at the black line, this is a cyclic voltammogram for oxygen reduction in a dry ionic liquid. So you see oxygen reduction to superoxide, and on the reverse sweep, you see the oxidation of superoxide back to oxygen. And here we also have ferrocene in as an internal reference. And what you can see is as you increase the relative humidity of the environment above the ionic liquid, and we do this by having a humidity generator that can give accurate relative humidity levels. So as you increase the humidity level to 13%, you can see in the green line that the current has increased slightly and the peak-to-peak separation has got a bit wider. And then as you go to 55% humidity, the blue line, and then a saturated humidity, 95%, you can see that not only have we increased the current quite significantly, up to about 3 to 4 times, but we've also reduced the potential for the oxygen reduction. And so this is because the reaction mechanism changes in the presence of water, and the oxygen reduction mechanism follows either a 2-electron process to hydrogen peroxide or a 4-electron process to water, depending upon the pH. So obviously we've gone from a dry reduction of oxygen to a wet reduction. So we wanted to see whether changing the structure of the cation and the anion of the ionic liquid has an effect on the oxygen reduction reaction. So we have chosen a number of different cations, the very commonly used imidazolium, and also these tetraalkyl ammonium and phosphonium cations, and a few other ones there as well. The cations are paired with an anion, and the most commonly used anions for electrochemistry are the tetrafluoroborate and hexafluorophosphate, and then also the more hydrophobic NTF2 and FAP anions. And anybody that's used ionic liquids before will know that they're very hygroscopic. So you just have to leave an ionic liquid out on the bench and come back the next day, and you'll see that the mass has increased. And this is because the ionic liquid is taking in moisture from the environment. And so the different structure of the cations and anions may have a different effect on the oxygen reduction reaction because they're more hydrophilic or more hydrophobic. So what Simon did was he measured the current response at different humidity levels. And here, this is a plot of the normalized current response versus humidity. So the normalized current is the current measured at that humidity level divided by the current in a dry environment. And this is to reduce the effect of the different viscosities of the ionic liquids. And so what we did first was to fix the cation. So we used a butyl imidazolium cation, and we changed the anion. And you can see here that at the very low humidity levels, there's relatively no change in the current response below about 20% humidity. And then as we add more humidity in, we see an increase in the current response, so it's changing over in the mechanism. And then as we get to the very high humidity levels or saturated ionic liquids, you can see that the current response has increased by about 2.5 to up to 6 times in the BF4 ionic liquid. And this is not unexpected, and it follows nicely the trend of the bulk solubility of water in the ionic liquids. And the bulk solubility of water is known to depend mainly upon the ion, the anion. So what about the effect of the different cations? So what we did is we chose a relatively hydrophobic NTF2 anion, and we looked at the effect of changing the cation. And here we have 7 different cations of all different chemical structures. And what you can see is that there is a much more dramatic effect on the current response at the low humidity levels. So between 0 and 20% humidity, if you look at the black line, in the ethyl imidazolium ionic liquid, we already see a 4 times increase in the current response. So it doesn't take very much water to change the reaction mechanism. And then as the cation hydrophobicity changes, you can see there's a different effect on the increase in the current. And the P14666, so the tetraalkyl phosphonium with very large carbon chains, you can see that there's relatively no effect on the current until you reach about 80 to 95% humidity. So this is the most hydrophobic cation that we have. And so in order to try to understand why the cation has the most effect on the oxygen reduction reaction, we have to look at what's happening at the electrical double layer. So when we bias the potential to reduce oxygen, the electrode has a negative charge. And in ionic liquids, the cation is known to form a dense layer on the surface to neutralize this charge. And then as you go out into the solution, you can see these alternating layers of anion, cation, anion out to the bulk solution. And Rob Atkin, who's at UWA, he's done a lot of the initial work on this. So we decided to have a look at what happens to the structuring of the layers in the absence and the presence of water. So in the absence of water, we can use an AFM tip, and we can approach the AFM tip towards the electrode surface. And as the tip goes towards the electrode surface, you see an increase in the force. And the force curve shows these discrete jumps. So these discrete jumps correspond to pushing or punching through the different layers of the ionic liquids close to the surface. And you can measure the distance between these jumps and you can relate these to the size of the ions at the electrode. So we saw that in all cases, in all the ionic liquids in a dry environment, we saw this very good structuring at the electrode. However, when we added water and we used a 40% humidity environment, we saw that in the more hydrophilic cation, the ethyl imidazolium, we saw a complete disruption of these, this layering, suggesting that water has had an effect to remove this nice dense positive charge on the surface. So we did a study on 3 different cations, so the most hydrophilic, the C2-Mem, the most hydrophobic, the big tetraalkyl phosphonium, and also one in between. And what we saw was that it was only in the most hydrophobic ionic liquid that we saw that the structuring was still present even with water at 40% humidity. And so what is happening here is we believe that the long alkyl chains of the phosphonium cation forms a very dense hydrophobic layer that effectively prevents the absorption of water at the electrode surface. So this means that we still get our reversible oxygen reduction, whereas in the more hydrophilic ionic liquids with the different cations, we have water present within the electrical double layer that then reacts with the electrogenerated superoxide. So this study really shows that it's very important to choose the right ionic liquid, particularly when the reduction product reacts with water. So what about the effect of different analytes whose reaction products don't react with water? So we studied initially a common redox couple in ionic liquids. So we actually chose decamethylferrocene instead of ferrocene because ferrocene has a moderate volatility in ionic liquids. So ferrocene undergoes a 1 electron reversible oxidation from the ion 2 to the ion 3 complex. And we can see in the cyclic voltammetry here a really nice typical reversible voltammogram for the decamethylferrocene. And then as we add water to the gas stream above the ionic liquid, you can see that the decamethylferrocene peak increases in current. But overall, the shape itself is very similar. We still have the same reversibility and we have the same peak-to-peak separation. So there's very little effect of water on the voltammetry of this redox couple. But we do see an increase in the current of about 35%. So you can see now the normalized current goes from 1 up to 1.35. And this is because we have an increase in the transport properties in the ionic liquid. So as we add more water, the viscosity of the mixture is lowered and the diffusion coefficient of decamethylferrocene has increased. Of course, this is also applicable to the oxygen reduction, but we saw up to a 6 times current response in that case. So what about another analyte, so a gas which oxidizes but which doesn't react, its reaction products don't react with water. So we looked at ammonia oxidation in ionic liquids, and this is known to produce protons and nitrogen as products. So you can see here, we're just showing the linear sweep voltammetry for this because it's an irreversible reaction. You can see the dashed line is the blank in the absence of ammonia, and then the red line is the response of 200 ppm ammonia in a dry ionic liquid. So now as you increase the relative humidity, you can see that the current response increases, and also we see a shift in the peak potential. And what you can see here is when we plot the normalized current, and we've done this in a few different ionic liquids, the normalized current increases by approximately double. So compared to the 1.35 that we saw for the decamethylferrocene, this is obviously a bit more. But we don't expect that water reacts with any of the products. So where is this extra current coming from? Well, what you can see here is that the potential window is actually coming in as we are adding water into the ionic liquid. And the potential window is giving us a current response that is adding to the current of the analyte. And so this led us to have a good look at what the blank ionic liquid looks like in the presence of water. So here is the voltammetry for the wide scan blank ionic liquid. So you can see in a very dry environment, the black line, you can see this relatively wide window of about 4 volts. But as we add even just 6% relative humidity, we decrease the anodic window quite significantly. And then as we add more and more humidity to the ionic liquid, we get a potential limit of just about 2 volts. So the potential windows are defined by the oxidation and reduction of the solvent or the electrolyte. And so what we did here is we looked at various different ionic liquids, and you can see that the potential window in a dry environment is about 3.5 to 5.5 volts, but in a wet environment, it reduces to about 2 to 2.5 volts. And what we think is happening here is that the behavior is changing initially from just small amounts of water in the ionic liquid to ionic liquid in water. So the potential window becomes mainly defined by the oxidation and the reduction of water. And so I note here that we are actually using very low cutoff currents. So you can see these impurities in the ionic liquids and they become quite obvious. I don't have any time to talk about this at the moment, but that's something interesting about ionic liquid solvents. So going back to the structure of the electrical double layer, then what we think is happening is that in a dry ionic liquid, we have these really nice dense structures of ionic layers at the electrode. But when we have water present, we can see, especially for the more hydrophilic cations, we can see that water can now partially solvate the ionic liquid ions near the electrode, and the behavior becomes much more similar to a conventional solvent electrolyte system. And I also note that we can actually electrolyze all of this water. So if we scan to a wider positive or negative potential, we can electrolyze the water, and then we have the potential windows defined by the ionic liquids again. So I think overall, it's really important for people using ionic liquids in any electrochemical applications to understand what's happening at the electrical double layer and also the effect of water. So I'd like to thank mainly Simon, who's done most of this work, my postdoc who helped out with the AFM experiments, and also a third-year project student, Taylor, who worked on the ammonia humidity stuff. So thank you for funding from my institute and also the ARC, and thank you all for listening.
Thank you very much, Debbie. I'll give you a clap on behalf of all the people that are muted. I think my questions were answered in chat already. I'm just going to give people a minute to ask any further questions that they'd like. I think you did a great job in explaining it so everyone's sitting there absorbing information.
Yes, good.
Yep.
Thank you to Simon as well for answering the questions.
Yes, no, he was awesome. So I might ask us maybe, I'll put a few announcements up that we've got, and then we'll see if we've, I'm sure questions will come in the breakout rooms in any case. Let me...
Sure, no problems.
Oh, there we go. I can share screen. There we go. I'll just put the announcement up. Okay, so the next webinar is in a fortnight. P, can you sure find it? Locating transition states from above. A talk from Terry Field Theodore, which sounds really intriguing. I like the title. And we're also going to try something a bit new because we like to vary it up here. And we're going to be doing multiple student talks. So sign up here. I'll put the link in the chat as well, if I can figure out how to do that. Sorry, just let me. Can I do that? Yeah, I might be able to. No, we'll have to wait. Okay, so I'll put the link in the chat in a moment. Honours students, remember we're running a session where you can get some feedback on your talks. So we're going to run a special session for honours students so you can do the 15, 20 minutes, whatever your universities does. Note that the newsletter information on the student conference, division meeting and Hush symposium were out of date. Apologies for that. As you can imagine, it's a bit of a changing environment that's happening at the moment. And let me see. Oh, we've got some questions. So some questions in the chat. So I'm just going to put the link thing there. Sorry, okay, so this is the link. I think we'll leave Debbie to answer some questions in the breakout room. We've got some great talks. Thank you very much. What we're going to do now is we're going to split off into breakout sessions. I know many people have meetings. Makes sense. See you later. If you do have some time, I would encourage you to stick around, especially some of the students. We're generally friendly here. I've got a discussion topic, but feel free to move it along. You know, talk about whatever you feel like. But the topic of interest that I've selected today is, how do you select your research topic? So as a student, as a postdoc, as a supervisor, how do you decide what you're going to work on? And this might be a good opportunity to ask Amir and Debbie some further questions. I'm going to break us into chat rooms in a moment. Senior members, can you just help me out by just facilitating the chat, because you need a little bit more structure in these things than you do in person. Okay, so I'm just going to start some breakout rooms.